All right. So for this video, guys, this is what we're going to be doing. First thing you should do is copy down these 3 questions into a Google Doc. So I'm going to be showing you guys a video in a second, and you're going to be answering these 3 questions at the beginning. So if you can, pause the video right now and copy them down. We'll get into that in just a moment. I also have Jazz here with me for the lesson, so if you hear somebody talking or if I ask some questions, you're going to be hearing Jazz's voice. So, that being said, you guys should have paused the video by now, copied down these questions, so I'm going to start talking. So, in this video I have right here, I'm going to be showing you guys activation energy and catalytic reactions today. And here I'm mixing 2 chemicals together. What you see at the bottom here is a chlorite solution. I'm not going to show you guys exactly what chemicals I used because this one can be dangerous. Actually, it's very, very dangerous. You'll see in a second. And in this yellow bottle is called brake fluid. So when you're looking at this first question, what do you think is going to happen? You guys can make a guess. I have Jazz here, so I'm going to be asking Jazz what his idea is. So Jazz, what do you think is going to happen?
Um, I think that heat is going to be released. That's my
Heat's going to be
guess.
released. What type of reaction do you think is going to take place? Out of the 5 we talked about, which reaction is going to take place?
You mean okay.
Single, double,
Yeah,
synthesis, decomposition, or combustion?
I don't think it's going to be combustion. Well, I'm pretty sure because you said. So I go with double replacement.
Could be. And the last one is, how long do you think this reaction is going to take? Without looking at the other YouTube video, for people who are listening to this later on, don't cheat. Suggest how long do you think it's going to take?
I'm gonna go with 5 seconds.
5 seconds. Nice. So, I can answer that first one because I'm going to show up to you anyway. It's going to actually take 14, almost 15 minutes for this reaction to take place. So I'm not going to be playing this whole entire video. If you guys really want to watch it, it's on my YouTube channel for this class page. So if you go look up my thing, you can find it yourself. If you really feel like watching 14 minutes of a reaction happening, be my guest. So when we start here, you can see I have my chlorite ions here, and I just mixed in the brake cleaner. Now what you're seeing me here is I'm just setting up my camera station, give it a quick swirl to make sure it is mixed together, and I'm going to let this just record. So I did this outside of my lab I built from my own house, so you can see that it is going to be a little bit dangerous because I'm doing it outside. Don't worry, I did have a fire extinguisher next to me, so just in case anything happened, I was ready. I also had stuff to cancel this reaction out. So as we go, we can kind of observe what's going to happen here. I'm going to start skipping a little forward. So at 2 minutes, again, nothing much has happened. So keep going further. At almost 4 minutes, you kind of see like some swirly stuff going around here. Nothing awfully a lot to really write home about. This stays about the same as my YouTube video loads, so I'm skipping around. For most of the time, even go up to 9-minute mark. Again, nothing really has changed. So now we're going to skip ahead to about the 12-minute and 20-second mark. And now we're going to watch carefully as what's going to happen here. So as we're watching a solution, I want you guys to keep an eye on the white powdery stuff down here and the liquid on top, because something is going to start happening now. As you observe, what are we seeing here? So Jazz, you're here. What do you kind of seeing starting to come out?
I'm making my screen. A little bit of steam.
A little bit of steam. So
And
right about now, it's starting to pick up. And
yeah,
just starts to react instantly with one another. Now keep an eye on what's happening down here. As you can see right down here, I'm going to go back in a second to go and slow it down. We saw that the white powder in the bottom is starting to turn what color? Jazz, you can answer this one for them.
I think
I know it's hard to
black.
kind of see. You have to wait for
I
the
see.
smoke to clear sometimes.
I see some black.
Some black, some brown, and a lot of smoke being produced here. So as we keep letting this go, we can start seeing it now turn really brown up top and black going through the whole entire mixture. We kind of see that all the powder around here is turning colors. Now, I grab the phone so we can actually see what's going to happen on the other side. Got a little too smoky on that side. I would not recommend this lab being downwind of it. It will smell pretty bad. So you can see on here, everything is starting to turn black. Now, what kind of reaction turns things black and usually produces a lot of smoke?
Combustion.
Yep, this reaction is actually a combustion reaction. I used a smaller dose so it didn't catch fire, but if I were to add a little bit more brake cleaner or brake fluid while I was doing that, it would actually catch fire. That white smoke is just incomplete combustion happening. It was also really cold last night when I was doing this and kind of raining outside, so I wouldn't expect very much stuff to happen. But as we saw that, it started reacting very, very fast. Now I want to go back to that point right before it started to react. So I'm going to slow this down a little bit just so we can see what's going on here. So right when, at this point, I want you guys to watch here. Watch as right when you see it start to boil over, watch what happens to the powder here. You see all this stuff start bubbling and starts going down further into this solution down below. It actually mixes together. You can see right here that all that liquid started to go underneath the powder. And that's really what set off this reaction. Now, what actually happened here? Well, there's two things that happened. The first thing is that we're going to be talking about the last type of reaction rate, which is catalysts. Now, catalyst, as you guys can read here, if you guys need to pause the video to get caught up on notes, I'll be slowing down for Jazz to take notes as we're going through. You will see this stuff happen. So first off, a catalyst is a substance that allows reaction to occur faster or at a lower temperature. Now, if you remember during the popcorn lab, we all did our regular popcorn and we had changed the volume, the temperature, the size, the concentration, and then we had the Jiffy Pop. Now, when you guys did all the other the experiments, you guys had no popcorn being burnt or very, very little. When we had the Jiffy Pop one, that's when a lot of the labs groups burned their popcorn. And that's due to this catalyst reaction here. What's inside a Jiffy Pop is a lot of oils and butter and salts that will, first off, make the popcorn taste better, but also acts as a catalyst. Because oil can heat up a lot faster than air or anything else, it causes that reaction to heat up and start to react faster. If you guys remember when we did the Jiffy Pop, in almost like 40 seconds, everything started to pop. While in other cases, it took like a minute for them to start to pop. Now, catalysts are not used up in the reaction, they're just part of the reaction. Catalysts lower the amount of energy needed for a reaction to occur or bonds to break. And catalysts are neither a reactant or a product, they are written above the arrow, just like how it is right here. I'm actually put in presentation mode so you can actually see all of this. So you'll see this V2O5 molecule being the catalyst. This is how we make our sulfate solutions. As we kind of take this ion right here, we mix it with both those, and we start to get sulfate ions to form. Now, if we don't have this here, this reaction would actually not take place. This right here will not happen. It'll stay as oxygen gas and sulfite gases until we add this metal in there. Then we are allowed to have this happen. All right. So if you guys a second to get this copy down. Jasmine, ready? Please tell me, and then I'll move on.
All right. I think I'm ready.
Okay. So the next thing we're going to talk about is just having a little bit of examples. So in here, this is going to be nitrogen and hydrogen to form ammonia. What are we using as the catalyst here? We're using the, Jazz, you can answer,
Oh, Fe.
the iron molecule. If we don't have iron here, no matter how much nitrogen and hydrogen gas you have there, you will not be actually forming anything. Nitrogen gas and hydrogen gas will sit there and just bounce off each other and kind of just react around and be like, nah, man, I don't need you right now. Catalysts are like, you can think of it as the friend of a friend. So it's like if you go to a party with a friend, you have don't know anybody else there, and then your friend that you came with was like, hey, man, I know that you know me. I meet my other friend, Charlie, and now you and Charlie are friends. So it's kind of that person in the middle that links other people together. Again, we have ethane, and steam produces ethanol, or pure alcohol. Now, there's something that we need to actually put in here, and this is why making gasoline or making alcohol from gasoline can be kind of expensive and kind of dangerous and a little bit of a hard process to go through, because you need this phosphoric acid molecule right here to be used as a catalyst. When you mix these two liquids together, they'll just sit there and kind of separate. As you guys have seen before, ethene is more of an oil, and H2O is water. You know that oils will always float on waters. So how can you get something to react when they are not wanting to react together? Well, you gotta use something that it's going to want to mix those things with. In this case, phosphoric acid works perfectly. So, Jez, have any questions so far on the catalytic reactions?
No, I'm good.
Okay. So now we're going to go see what happened in our lab that I just showed you on that first video. Now we're going to be talking about what's known as activation energies. Now, activation energy is this magical thing. Now, why I say it's magical is that you can make stuff react faster or slower depending on what catalyst you put in there. So on here, this first line, we have the reactant with no catalyst. Right here, we have no catalyst here. We go up, it takes a lot of chemical energy to get to here. Then after we get there, it goes away and goes down. Now the other form, the red one, is a reaction that is with a catalyst. Now look how much difference in the energy we needed. This just started, went here, and went down. It's like a quick bump, and I was like, okay, we're done. So, an analogy that I'm telling you guys about this is like waking up in the morning. Now, if anybody here is a coffee drinker or energy drinker or whatever you do to get yourself awake, it could be a run, it could be whatever you do in your morning routine to wake yourself up. This first blue line is trying to wake up on your own without any stimulants. For me, this blue line will be me waking up and not drinking coffee. It takes me a long time to get awake. Then after I'm awake, I'm like, okay, now I can get done with my stuff I want to get done today. This red line, however, is if I were to drink coffee. So I wake up here, and I drink my coffee. As I'm drinking my coffee, I'm becoming more awake. And to this point where I'm like, okay, I can get done with my work, and I go and work. So in our case, of our reaction as before, I did not put a catalyst in there. So what happens is I had to wait this whole long time for the reaction to take place. Now, if you look back at that video, you probably didn't know, but there was chemical reactions happening all the way through here of our reaction. And it was like the two ions were like, yeah, okay, we'll kind of talk, we'll kind of react. Here we're like not reacting, we're going to be somewhat reacting, somewhat reacting, somewhat reacting. Then right up here is when that friend of a friend takes over. And we're like, whoa, we actually like each other. And they start to react, and they start to react very, very, very fast. So it starts going down. If you want to know what the actual reaction rate for this one looks like, we are actually starting off with a very high one. So if we're going over, we'll do reaction. Reaction. And time. So if I make a graph for reaction and time, so as we are going, as time goes up, we are building up, building up, building up, building up, building up, and we're just continuously going up until we hit that 12-minute and 22 mark. At that point, 12:22, we saw something happen. At 12:22, we started seeing smoke. At that point, we are starting to actually level off. Until we hit that point where we had, I think it was like 12:50 or something like that, where the reaction started to really occur. When you saw that smoke billowing out, you saw the changing of color, you saw all that fun stuff. That's when that reaction started to take over and was like, finally those reactions were waking up. They wanted to move again, and they started to react with one another, and then it started to go really, really fast. As you saw, it only lasted roughly about a minute. So it took all this time to build up. Then it started reacting, then it just went really quick down with the reaction into nothing. So that being said, the reaction progress happens as we go across. The chemical energy needed to break those bonds appear. Now, if you look down here, it's just saying that this blue one's not with a catalyst. That was our SO3 molecule here, or SO2 molecule plus O2, and our SO2 molecule with our catalyst. So that's all I really want to do for today. It's just a short one. I'm not getting into the next part. The next part we're going to be talking about is going to be equilibrium. This is going to be our longer time of notes. This will probably be next week. We're going to be talking about that. But what I want you guys to do now is to answer these few questions. Copy them down to your Google Docs. If you can submit them to me, awesome. I'd really appreciate these because I do want to know what we're feeling about this stuff, especially for people who are not here. And the last question is more of a personal question for me. I know I've been posting a lot of YouTube videos about this. This is what I like doing. It's the way I feel most comfortable presenting information to you. If there's other ways you would like me to get the information out to you, please, under that question, feel free to give me suggestions. But that's all our notes for today. If you guys can get them done for me and turn them in, that'd be awesome. Thank you guys for your understanding of all this stuff going on, and have a great rest of your day.